So, good evening, guys. Today's session is about TF-IDF vectorization. Basically, it is about text vectorization. So, why do you think that we vectorize text?
Ma'am, because the machine is not able to understand our own language like English or any other language directly. So we convert them into vectors or numbers. So it's easy for machine to understand what the what the thing is about.
Yes, that is correct. So, any other answers? Any of you know about it? Okay, so basically, machines can't process raw text. So they need numeric representations. That is basically binary, 0 or 1. So text vectorization means that converting the sentence into fixed length numeric vectors. So before any text data that can be used for classification, for example, that would be spam detection, uh, for clustering. Example would be topic modeling, translation, sentiment analysis, etc. The first and foremost thing is that it needs to be converted to numbers, specifically to fixed length numeric vectors. Since the machine cannot understand the sentences, so it needs to be converted in a binary form so that the machines can understand it. So if we consider the sentence, the movie was fantastic and inspiring. To you, this is full of emotion and nuance, but to a machine, it's just that it is everything is separated by a comma, and this has no measurable structure for math operations, and it cannot be compared to another sentence like cosine similarity, and it also cannot be fed directly to a model like logistic regression or SVM. So the basic agenda for this is to convert the sentences in a binary form and a fixed length numeric vectors so that the machine can understand what the sentence is about. So what is a vector? So a vector is a list of numbers, like as you can see, as follows. Basically, the vectors are uniform in size. That means fixed length is there, and it allows mathematical operations like distance, dot product, etc. And it also represents key features of the text numerically. So imagine you are recommending books. So to compare books, you can't just read the blurb. You need structured info like genre, author, and rating. So similarly, to compare or process sentences, we need to convert them into numeric summaries. So the benefit is that it has the compatibility with ML models like SVM, logistic regression, that requires numerical inputs. So that is one of the benefit that it has, comparability. So it is also one of the benefit because vectors can be compared, for example, using cosine similarity, and mathematical operations are also a benefit for it because you can cluster, classify, calculate, and calculate the distance between the vectors as well. And one more benefit is there for feature engineering because vectors can capture meaning, frequency, and importance of words. So there are three methods to vectorize a quick intro. First is bag of words, that is BOW. So it counts how many times each words appear in a document. TF-IDF means that it weighs word based on how important they are in the document relative to the corpus. Third is word embeddings. For example, that would be word to vec glove. So it learns dense semantic vector representation of words. So now we'll start with bag of words. So basically, bag of words is a technique to convert text into numerical features based on the presence of words, the presence of frequency. So it completely ignores grammar, word order, and semantics. You can think of it like a shopping list. You only care what items are in the bag and how many times, not in which order they were picked. So, real life analogy for this would be like, suppose two students submits essays. You want to check what they wrote about based on word usage. So, student A is that I love natural language processing and machine learning. Student B is that machine learning is fun and I love NLP. Even though they say similar things in different ways, bag of words will focus on the word used, not the sentence structure. So, basically, bag of words is a technique used to convert text into numerical features based on the presence of words and the frequency of words. It completely ignores grammar and word order and semantics. It basically sees that how many times the number of words has been used. So count vectorizer is a class from skitlearn, and it is used to convert a collection of text documents into a matrix of token counts, commonly known as the bag of words model. So the definition for this count vectorizer is that it transforms the text into a vector where each column represents a unique word that is taken from the corpus, and each row corresponds to a document. So the value is the count of how many times the word appears in the document. So the significance for count vectorizer is that it transforms text into a vector where each column represents a unique word that is taken from the corpus, and each row corresponds to a document, and the value is the count of how many times the word appears in the document. And the use cases for this would be feature engineering for task classification, input to ML models, that would be logistic regression, SVM, etc. Document similarity comparison is also used for this. So okay, so what does count vectorizer does? So basically, it tokenizes the corpus, splits into the words, it removes duplicates, and it also builds a vocabulary of unique words, constructs a sparse matrix counting word frequency per document. So as you can see, love and loves are treated as different tokens because no limitation is applied, and all are lowercase because default behavior of count vectorizer is there. So the vocabulary size, so it grows with the number of unique words in corpus, and as you know that no order awareness is there, BOW ignores the word order. So for example, NLP loves me or me loves NLP. It is the same for bag of words because it ignores the order. So sparse representation is that most entries are zero if the vocabulary is large. And it is also easy to use. It works well for simple tasks like spam detection, topic modeling, etc. And here comes the limitations of bag of words. So basically, no semantics. Love and adore are treated as unrelated. No context. the bank money and the bank river gets the same weight, because as you already know that river bank is also, like, bank is also called as river bank as well. So there is no context between the words, it gets the same weight assigned to it, and it can be sparse and memory heavy with large vocabularies. So where is BW is useful for real world scenarios? That would be email spam classification, keyword search, document similarity, basic. So I have a question. Do you guys can answer it? Because what would happen if we added the punctuation? So what would happen if we added punctuation?
Uh, so if we add punctuation to bag of words, it will basically like treat those as sentence as well, which would like compromise with the efficiency.
Okay. Any more answers? So that is correct. Because punctuation will be treated as a token if it is not removed. So if the punctuation isn't removed during the pre-processing, each punctuation marks becomes a separate feature, and it will like adding the punctuation makes the features vectors more sparse, and like offering little predictive value is also there, and possible misinterpretation would also occur, because as you know that punctuation often doesn't carry meaning in isolation, so keeping it may reduce model performance. So the second question is that why might bag of words not work well for a chat box?
uh, Chatbot, uh, in the for the case of chatbot, they analyze the structure of sentence, sequences of words and meanings, including grammars also, but bag of words neglects or ignores these things, so bag of word technique is not applicable for chatbots, I think.
Yes, that is correct. Any more points for this? So basically, there will be no understanding of word order because, as you know, that bag of word ignores the sequence of words. So, for example, I am not happy and I am happy look very similar, but even though their meanings are quite opposite. So, chatbot needs to understand the context and the syntax, which bag of words cannot provide. So, no contextual understanding is there, and it does not understand that bank in river bank is different from bank in money bank. And for this case also chatbots needs to understand the contextual meaning which bag of words lacks, and it also has some fixed vocabulary and poor generalization. So bag of word uses a fixed vocabulary based on the training data. So if a user types something new or misspelled, the chat box may not recognize it. And chatbots must handle a variety of ways to say the same thing. And high dimensional sparse factors are also need like they also need to be considered because every unique word is a dimension and it creates a large sparse vector, and it is inefficient for real time responses in chat box. One more major point, because no handling of synonyms or semantics is there. Hi, hello, hey are different in bag of words even though they mean the same. So this leads to rigid or unnatural responses, and no memory of past conversions are there because bag of words works on one message at a time with no sense of dialogue history. And as you know that chat box require dialogue management, which bag of words doesn't provide. So what's better for chat box are that word embeddings could be better, transformers could be better for this, because these all capture order semantics and can be trained in a dialogue flow. So, what real world systems might still use bag of words? What do you think?
Resume screening application.
Okay. Any more answers?
ETS system.
Okay.
It is used to detect emails with common spam.
Yes, that's correct.
It can like also be used for like a document categorization, like
Yes.
keyword searching that goes through the document.
Yes. So basically, it is used to resume screening tools, SMS filtering on devices, and you can say like and as well for sentiment analysis, that is for basic purpose. They can like simple review can be done for this. Um, Spam detection as told. So these are the categories of real world system that still uses bag of words. So what is TFITF? So capture how important a word is to a document in the context of a collection of documents. So TF-IDF stands for TF stands for term frequency and IDF stands for inverse document frequency. So together they form a weighted score that shows how important is a word to a particular document while reducing the weight of common words that appear in many documents. So as you can see how often a word appears in a document, this is the formula that we'll be using. So by using the formula for this sentence, we are calculating how often a word appears in a document. So for love, by putting the values in the formula, the value is coming 0 0.4, and for machine, it is coming 0 0.2. So by inputting this formula, this is how term frequency is calculated. So here comes the inverse document frequency, that is IDF. So this will be the formula that we will be using to calculate inverse document frequency. So words like the is appear nearly in all documents. That means that it has low IDF. And words like transformers, vectorization appear very rarely. So that means high inverse document frequency. So the TF-IDF score is calculated by using this formula, that is term frequency into inverse document frequency. So as you can see this, I love machine learning. Machine learning is fun. I love deep learning. So less focus on term learning. So it appears in all three documents. As you can see, learning is appearing in all three documents. So the inverse document frequency will be low. But it appears once per document. Then TF is normal, that is 1 by n terms. So even though learning is common, its TF ITF score is low due to its high document frequency. But the word deep appears only once in one document, so its IDF is high. That means higher TF IDF score. So what is TF-ID vectorizer? So TF-ID vectorizer is a class from sklearn feature extraction.txt that converts base the text documents into a TF-IDF matrix, which reflects not just how often words appear in documents, that is term frequency, but also how important they are across all documents, that is inverse document frequency. So term frequency means that how frequently a word occurs in a document, and IDF means inverse document frequency, downweights common words across documents. So the use cases for this would be email classification, document similarity, search engines, and sentiment analysis. So advantages of TF-IDF over bag of words. So word frequency is there in both of them, but word, as you know, that bag of word lacks word importance, but in TF-IDF it is there, so it does not lacks. And as you can see that common word separation is not present in bag of words, but it is present in TF-IDF, and it is also suitable for relevance, that bag of word is suitable for basic search, but TF-IDF is suitable for information retrieval, ranking, and etc. So basically, TF-IDF gives each word a relevance scores. It combines local importance, that is term frequency, and global rarity, that is inverse document frequency, and it is great for task classification, filtering, and search. So basically, the feature output for bag of words is count vector, but for TF-IDF it is weighted floor vector. Common word biasness is high in BOW, but TF-IDF has a down-weighted. And the interpretation for BOW is simple but shallow, but TF-IDF it has more meaningful interpretation over there. So basically, vectorization converts text into numbers. Bag of word frequency only is there, but for TF-IDF frequency plus importance is there, and it is both used in spams, filters, recommendation search engines. So intro to the word embeddings. So word embeddings are a natural, a dense vector representation of words that enable machines to understand language in numerical form. So the static embeddings are word to vec and globe. Second is contextual embeddings like BERT and how they work. So learn word meanings from large corpora. It uses co-occurrence statistics or predictive models, that is scriptgram in word to vec, produce dense vector representation, usually 50 to 300 dimensions, to word bat. Sentence A, he swung the bat. Sentence B, the bat flew at night. Static embedding, both bat have the same vector, which is incorrect in context. So basically, contextual embeddings generate different vectors for a word depending on the sentence it is in. They are derived from transformer based models like BERT that read both left and right context. So, how they work? They use transformers to process entire input sequences, output embeddings for each word based on its position and surrounding words, and vector change with context. So, word2vec and Globe are classic word embedding models that produce a fixed vector for each word regardless of context. Word2vec is based on a shallow neural network, uses either continuous bag of words or scriptgram, learns to predict surrounding words. Globe, that stands for Global Vector for Word Representation, uses global word co-occurrence count. It trains on a word co-occurrence matrix and factorizes it because these models capture semantic similarity. So the limitation is that the embedding is statistic. The embedding is static. So the word bank has the same vector whether it means a river bank or a financial bank. So that is the limitation for it. So now it is for BERT and contextual embeddings. So BERT, bidirectional encoder representation from transformers. It generates contextual embeddings. That means the representation of a word depends on the surrounding sentence. So how BERT works, it uses transformer architecture, reads the entire sentence bidirectionally, embeds each token considering full sentence context. So what BERT does under the hood. So when you pass a sentence to BERT, the process is roughly the tokenization, breaking down your sentence into subwords, tokens that BERT understands. Embedding lookup plus encoding, BERT converts each token into a 768 dimensional dense vector using its pre-trained knowledge. So the term word to vec is that it learns vector using local context via neural network. Glove is that it learns word vectors from global co-occurrence statistics. Bird is that it generates dynamic vectors based on full sentence context using transformers. Dense vector is that a compact vector with mostly non-zero values. Context aware embedding is that embedding that varies based on surrounding words. Wait a second, this is not. So over here we are using count vectorizer from a skill learn to apply bag of words. So the corpus is I love NLP, NLP loves me, and I love machine learning. And as you can see this, the count vectorizer, what it does is that it tokenizes, splits the text into words. It builds a vocabulary from all documents and it counts how many times each word appears in document. So X to array that basically converts the sparse matrix into a full matrix. And the vectorizer dot get underscore feature underscore names underscore out gives the column names, that means the vocabulary. As you can see that the sentence one is I love NLP. For love, row 0 you can see that love is given 1, NLP is also given 1. Sentence 2, NLP loves me, as and in this also loves is given 1, Me is also given 1. NLP is given 1. And row 2, you can see that that is sentence 3. I love machine learning. For this, love is given 1. Machine is also given 1. Learning is given 1. So what happened to I? So count vectorizer removes stop words like I by default, that is lowercase is equal to 2. Lowercase is equal to true, and the punctuation is stripped. So it treats I as unimportant.
Ma'am, if instead of I, we comes as the first word in a sentence, then the W will be in capital. So in that case, we shall also be ignored by
Sorry, sorry,
this
sorry.
model.
Can you come again?
Like in this case, I is neglected by this model. But in case of me or we, if we comes at the first position of a sentence, first word in of a sentence, then the W becomes capital. So in that case, what will happen?
So me will not get ignored because the only stop words are removed, including like you can say that like because unless like you need to express you need to set it actually like in our current example me is included, right? You can see that in like it is not there, I is only there, that is a stop word. So if we use like count vectorizer stop word is equal to English, then all the English stop words are removed, including I, me, we, you. Then it can be done if we use it. We need to
Okay,
use a command like count vectorizer stop underscore words is equal to English. Then everything will be removed.
okay, thank you.
Okay. So basically in this we are using TF, that is term frequency. That means how often the word appears in a document, and using inverse document frequency, how rare the word is across all documents. So a word is important if it is frequent in one document, and it is less important if it is frequent in many documents. So as you can see the terminal output breakdown, each row is equal to one sentence document and each column is equal to a unique word, and each value is equal to TF-IDF score, and TF-IDF score is calculated into term frequency into inverse document frequency, right? So as you can see that the interpretation of row 0, that is high scores for love, machine and learning is there. So these words are important and unique to document 0, that's why these scores are high. And as you can see that row 1, it contains fun, is learning, machine, and love is not present here, so that's why it is 0. For row 2 also you can see that deep has high TF-IDF because this means it is rare across all documents but common in this one. So why values are not integers like bag of words? Because TF-IDF gives weighted values that are not simple counts, and value ranges from 0 to 1 depending on frequency and rarity. So we are using TF-IDF, which gives more meaningful and importance. Filter out common words, that is low IDF. Great for tasks like document classification, search and relevance ranking. So that this is for term, like this is for TF-IDF vectorizer. So in this we are using BERT. So from transformers, import BERT tokenizer, BERT model that loads the required libraries. Then we are loading the pre-trained BERT model. So BERT base uncased means that lower case version of base BERT model is used, and model.eval, it tells the citors that you are in inference mode, not in training mode. So then we are going to tokenize the input sentence, that is the sentence is that he sat by the river bank. So the tokenizer converts the sentence into the input IDs and attention marks for the model. And it also breaks the words like bank into subword tokens if needed. So the token generated for he sat by the river bank would be like everything will be separated by comma, and even the punctuation mark will be considered as a single token. So including that as well. Then the BERT model output is given. As you can see, outputs. So this is used for model tokens and embedding. This is a tensor of tensor of shape, that is one sequence underscore length, that is 768. So one is the batch size, sequence underscore length is the number of tokens, and 768 is the bird's hidden size, that is vector per token. So in the document itself I have told about this 768 that is used. Then the CLS token embedding is there. So bird prepends every input with a special token, that is CLS. This token embedding is often used by summary of the sentence. So we are printing the 768 dimensional vector corresponding to the CLS. Then the attention marks comes, that is mean pooling for sentence embedding. So over here we calculate the mean of all token embeddings, ignoring pad and tokens none here. So this gives a sentence embedding that represents overall meaning of the sentence. So these are the tokens. Embedding shape is size is 1. Sequence length is 9, that is number of tokens. And 768 is the dimension. So CLS token embeddings is that long tensor of 768 float values, like as you can see in the screen, that is minus 0.0496 and so on. There will be total 768 values. So it is used as sentence representation in many classification tasks. So also the mean pooled embeddings is also there. Okay, so the mean pool sentence embedding is also present. So it also represents a 768 dimensional vector. It represents average meaning of all the tokens in the sentence, and it is often more useful in semantic similarity or sentence level tasks. So mean pooling means that average embedding of all tokens. please go through the code. And for this, you need to install transformers. So that's it for today. I will share the documents and you will receive it shortly.
Thank you, ma'am.
Okay, thank you.
Thank you, ma'am.
Thank you.
Thank you, ma'am.
Okay.